All right, welcome to the third lecture um, on robotics. We are continuing our discussion on industrial robot manipulators and particularly different types of robot manipulators. Um, Last week, uh, I showed you this slide. There are about 5 different types of manipulators. Uh, so at the top is the Cartesian coordinate robot, and then cylindrical, spherical, Scala, and articulator. So when you see these 5 different types of industrial manipulators, you will notice very quickly the first 3: Cartesian, cylindrical, and spherical. So what is it that is familiar to you when you see these words, Cartesian, cylindrical, and spherical? Don't you remember something that you have already studied about, uh, and you recall it through these words, Cartesian, cylindrical, and spherical? So what is that? Anybody who's having some idea? By the way, can you hear me well?
Yes, sir, we can hear you.
Yeah. So when you were studying about coordinate systems, right, in mathematics or maybe some other module, you definitely have learned this. There are different types of coordinate systems, right? Cartesian coordinate system, cylindrical coordinate system, and spherical coordinate system. Okay. So Cartesian coordinate system is uh, a coordinate system where you have 3 axes orthogonal to each other, x, y, z, and using the axis coordinates, you can locate any point in the space uniquely. So that is what is called the Cartesian coordinate system. Now, Cartesian coordinate robot is a robot manipulator which has 3 different axes, okay, orthogonal to each other. And in the same way that you locate the point in Cartesian coordinate system, you can locate the endpoint of the robot manipulator using 3 coordinates, x, y, z. So therefore, there's no reason to pick any other word for that robot than saying or naming it Cartesian coordinate robot. Okay, and we saw that last week, and also the video, right? You see this video. Robot has 3 axes. It goes back and forth, sideways, there is left and right, and it also goes up and down. Okay, so this resembles the XYZ orthogonal axis coordinate frame. So that is why we call it Cartesian coordinate robot. And the next one is cylindrical coordinate robot. So now you can recall your memory about cylindrical coordinate system, right? So in cylindrical coordinate system, you have different way to locate a point, right, within the coordinate frame, right? So you have the rotary axis, which gives you an angle, whereas in Cartesian coordinate system, you don't have rotary axis, right? So you have the height, right? You have the length, that is the radius, and the angle. So if you look at a cylinder, right, with different heights, different sizes, any point on the cylinder you can locate using the 3 coordinates: the height, the radius, and the angle. Okay. So coordinate system is a entity which provides you some mechanism to locate any point in the workspace using a number of coordinates. Okay. So if I show you a cylindrical coordinate robot, right, it is this one. I think we saw this last time. This is a cylindrical coordinate frame. This is a height, right, height adjustment, and then this is the angle, right, height, angle, and another distance. That is the radius. So height, angle, and the radius, 3 coordinates. Okay. So the height and radius here are actually linear coordinates, linear, right? So in order to adjust these coordinates, you need to have a linear actuator, which does not rotate, but moves linearly, up or down, left or right, in or out, right? It's a linear motion. But to control the angle, you need to have a rotary joint. So it's like a motor. You have the stationary part and also the rotary part, right? And there are bearings to keep them in place, same axis, but one is moving, the other one is not moving. Okay. So similarly, in robots also, you have these joints where one link is, I can't say stationary, but relatively stationary. With respect to that link, the following link is moving, right? So in robotics, we have a shorthand notation for the manipulators, right? If the manipulator has all linear joints, right, or prismatic joints, like in case of XYZ Cartesian manipulator, we give it a short name PPP, prismatic. Prismatic is another name for the sliding joints or linear joints. Okay, PPP. So using the same shorthand notation for the cylindrical coordinate robot, the name is RPP. There's a rotary joint and 2 prismatic joints. Okay, right. So if you continue the same argument to the next type of robot, which is what? Spherical. Okay, now in case of spherical, you need radius and one angle which is on a certain plane. Let's call it a horizontal plane, and then you have another angle in the vertical plane. Okay, so one angle in the horizontal plane, one angle in the vertical plane with respect to the horizontal plane, right? You can have so many vertical planes, but any one of them, right? And then the radius. Okay, so in that case, you have one linear joint, one length, and 2 angles. So therefore, that robot, the shorthand notation for that robot is one sliding joint, one linear joint, and 2 angles. So it is RRP or PRR. Okay. So if I show you a robot like that, right, it's hard to find spherical robots. Very, very hard to find. Nobody wants to manufacture, sell, or use spherical robots, and they are only for academic interest. Okay, practically there's no such use because there are other um, simpler robot mechanisms to do the job rather than having to deal with spherical ones, right? And again, the coordinate frame, you remember the spherical coordinate frames you have studied, one distance and 2 angles. Okay, that is the spherical coordinate frame. So These are somewhat legacy manipulators, right? After that, we have two very popular robot types, SCARA robot and articular robots. In fact, uh, if you look at all these five, right, what do you think is the most widely used type in the world? Any answers? No answers. Actually, I need some sort of interaction from you guys, right? Because you are not kids, right? You need to be able to generate some thoughts, right? Even though you don't know perfect answers, you need to be able to logically think and respond, right, to the questions asked, right? You can be wrong. That's okay, no? So if I don't have any answers, I think all of you are wrong, right? So therefore, try to get engaged. Um, uh, at least to some extent. If I ask 10 questions and if I get no response for all 10, it's pretty boring, right? Delivering lectures. And that is not the purpose here. Lecturing, I can give you actually, if you do not interactively, right, I can give you the lecture note and ask you to study, read. If you want that, then that will also possible. Why we spend time talking to you, trying to explain you is to get you inspired. So get you to talk, get you to think, right? That is the whole purpose. Uh, so right now I don't get that sort of interaction. So that is a bit of worry. So articulated robot, I'm sure you have seen a lot of robots. I have shown you a lot of robots. On the internet, you have seen a lot of robots, right? So articulated type is the most widely used one. So there's no question about it. Why you cannot guess it? And I don't know. It's unbelievable, right? Scara is again kind of articulated, but not exactly articulated. It is the second most widely used one, or Cartesian robot. Cartesian ones are also used very much, but Cartesian robots are not very generic ones. You can use them for very specific purposes only, whereas Kara and articulated you can use for um, applications in general, particularly the articulated one. So you can use an articulated robot for almost any application, right? And you have seen why, right? In the videos I showed you, you saw all articulated robots, all rotary joints, right? uh, employed for various applications like cutting, welding, etc. So let me show you what the SCARA robot is, right? SCARA robot is something like this. So it has one rotary joint over here and a second rotary joint over here. They are both same parallel axis. This one and this one, they're parallel. Okay. And then over here, you have the vertical one going up and down. Right. So the all three axes are parallel and vertical in case of SCARA robot. That is the specific design feature of SCARA robot arm. So let me show you this video of a SCARA robot. Manufacturer is Adept and it's a Cobra robot. Yeah, so you saw that is one of the most fastest robots, right? In that video, in fact, the robot transferred 168 parts, small steel balls, in about 41 seconds, right? That is about zero point 0.2 seconds, at about 250 milliseconds, right? Per part. So under 1/4 of a second, it handles one piece. Okay, so that is and there's a very fast operation and performance, right? Now, I mentioned that this is a very special feature, right? A mechanical design. Can anybody guess what is that specific feature of SCARA robot and why that feature is so important? Can anybody guess any answer? Right. So if you look at this design, right, the two.
Is it a parallel combination?
Yeah, but it's not only being parallel. Go ahead. You have these two axes parallel. So why is it so important? What is the advantage of having it like that? Now, if you look at these two axes, right, they're both parallel, but more than being parallel, uh, they are vertical. They're vertical, right? So this axis is vertical, this axis is vertical. So when you rotate this arm, you rotate it around the vertical axis. When you rotate this joint, you rotate it around the vertical axis. Okay, so there's a motor here and there's a motor here. This motor provides a torque, right, to rotate the next axis and everything which is attached to that point outward, right, around the vertical axis. Here is the same. Think about you rotating something, right, uh, around a vertical axis versus you try to rotate something around, say, horizontal axis. You will immediately see there's some difference between these two, right? If you try to rotate your arm, right, on a vertical plane, you're rotating it. You're rotating it around horizontal axis. Okay, you lower your arms and then gradually raise your hands, raise your arms, right, like you when you do exercises. You will see initially it is easy, right, but when you rotate your arms by, say, 90 degrees, you feel it's difficult. And when you continue all the way up, your arms are straight up, again you will see it's bit easy. So holding the arms vertically downward position, vertically upward position is somewhat easy. But when you want to keep it horizontally, it's a bit difficult. Why? Why is that?
Gravitational effect.
Say it again.
Because of gravity.
Because of gravity. So the shoulder joint need to produce additional torque, right, to counter the gravity. To maintain in that position, we have to counter the gravity, right? So gravity is maximum when the arm is horizontal, 90 degrees. So that is why you feel it bit difficult. So that difficulty is there in machines as well. Okay. If a machine has a rotary joint and it has to maintain an arm connected to the rotary part of the actuator horizontally, right? It has to produce additional torque, right? To keep it that position. Compared with when the arm is in the lower position or vertically upward upright position. In this particular case, so now that particular problem is there because of the axis of rotation being horizontal. Axis of rotation being horizontal. Now in this case, the axis of rotation is vertical. So rotating like that. Rotating like that. So motor produce torque around a vertical axis, not around a horizontal axis. Therefore, the motor doesn't have to counter the gravity. Gravity is not actually seen by the motor because gravity works vertically downward. And the actuator here handles torques around the vertical axis. So there's no gravity around the vertical axis. It's along the vertical axis, not around. Okay. So there's no torque generated by the gravity, okay, around the vertical axis. In other words, the torque generated by gravity around the vertical axis is zero. Okay. Therefore, the motor doesn't actually see the nonlinear change of the gravitational torque. It will see something, right? But that is a constant thing. It's not a variable depending on the position, and it's not a nonlinear thing either. So it's a good thing to have vertical joints. And as a result of that, SCARA robots can work very fast. So speed matters, right? In industry, speed matters. So SCARAs are the fastest manipulators because of this reason. So there are a lot of applications. You can read about it through the lecture note, right? Then finally, we come to the articulated robots, most popular, very widely used type, right? So I don't need to actually show you these videos, right? Because it's something you know. So that is the articulated manipulator. There you have horizontal axis like this, right? And also vertical axis, and some axis you can't say either horizontal or vertical. So depending on the position, they get their orientation. But they're all rotary. They're all rotary. No sliding joints, right? They're all rotary. And can you pick up, if you watch carefully the video, a plus point, a very significant plus point of the articulated manipulators.
Uh, 180-degree rotation.
Uh, No, actually rotations in SCARA also, you can rotate quite a lot. Even actually you can rotate more than 180 degrees. You can access the entire workspace, right? That is what you want to say. So in case of SCARA and also the other manipulators also, you can access the workspace completely. There are certain areas that you cannot access. So every manipulator, there is a restricted area like blind points, right? Non-accessible areas. Here you can see this area is not accessible, right? What have you seen there in the video? And if you are a manufacturer, right, a manufacturing engineer, I think you like that feature.
Being able to access the same place using different orientations and directions.
Okay, that's a good answer. Very good answer. You can reach out to uh, almost any point, right, in the workspace, within the workspace, of course, right, with different orientations if you wish, right? So if you cannot approach it in one direction, you can approach it in a different direction, right? Yeah. So like, for example, human hand. Look at the human hand, right? If you cannot grab something, right, on a rack, so many ways you can approach that object, right? You can approach it from the top, from a side, from rear, right? Because our human hand has so many joints. Human hand has so many joints. So when you have so many joints, you have this ability to combine these joints in a different way in order to reach the same point, right? But different orientations. Yeah, that's a good answer. Anything else that you have seen as a feature, very significant feature of articulated manipulators? If you think of the space that it can access versus the size of the robot, you can get to that point. The physical size of the robot and the volume that it can access. What do you see?
Physical size is very small compared to the volume it can
Yes.
handle.
The physical size of the articulated arm is relatively very small compared with the workspace area or workspace volume. If you look at Cartesian robot, for example, Cartesian robot, the robot is big and the workspace is inside the robot. You know, the Cartesian one, it operates within itself, right? The accessible area volume is well inside the robot. Robot is bigger than the workspace. But when it comes to articulated, robot is very small compared with the volume. It can reach out like a snake, right? When a snake is like wound, it's a very small volume it takes, right? But when it is stretched, it can access a big volume. So these are the highlights of articulate arms. Thank you for those answers. Now I want to put all these different types of manipulators onto one sheet, like what you see here, right? Up front you have the Cartesian, and then the cylindrical, spherical one, and then you have SCARA, and then the articular, right? All 5 types. And we're gonna compare this one, horizontal resolution, vertical resolution, and try to figure out their pluses and minuses, right? And on this table, you can see the kinematic structure. If you read research papers, you will not see the manipulators like what you see here on the first column, right? Sometimes you do, but not very often. What you see very often is this kind of structure. This is the engineering representation or technical representation of these physical manipulators, right? So that anybody can understand, read and understand how they are connected. If you look at the physical structure, probably you don't know how many joints are there, where are they, what are they, types, etc. It is just a physical manifestation. But if you look at this one, these are technical drawings, right? You can see the joints and all. Okay, so this is the workspace of different types of manipulators. The Cartesian one, like this, and the cylindrical, spherical. When it comes to articulated, it's a very complicated workspace, very complicated workspace. Okay, very similar to the spherical robot. But I really want you to focus on this table here, right? What is this table? It says about horizontal resolution and vertical resolution. So this word is very important in engineering, resolution, right? So resolution is the smallest distance, right? You can incrementally change smallest distance. Okay. So any positioning mechanism, you have what is called the resolution. So in cameras also you have resolution, but that is a different one, right? What is the smallest piece of information you can capture? That's a resolution, right? When you have higher and higher and higher megapixel count, right, you have very high resolution as well. Now these are positioning equipment, machines, manipulators. The resolution here, the resolution is actually the smallest distance you can control. Okay, so let's say think about your control signal comes in discrete values, control signal 1, then control signal 2, then control signal 3, and so on. So what is the physical distance between 1 and 2? If the manipulator has been given position 1 command, and then you issue the immediate next command, let's say command 2, what is the distance, right? And out of all these distances, what is the smallest one, right? So if you do this for horizontal and vertical axis, right, you will see in Cartesian robots is a uniform thing. It's a uniform thing. X direction, Y direction, Z direction. Whatever resolution you have, it's not going to change from position to position. It's going to be unique, uniform, right? Rather. So that is for Cartesian. Cylindrical, your horizontal resolution decreases rapidly, whereas the vertical resolution will not change, right? If you look at the cylindrical one, if you look at the horizontal resolution, you are rotating something like that. If the radius is small, you have higher resolution. But if you have longer radius and then rotate for a very small angle here, you get sizable distance at the end point. Okay, so therefore your horizontal resolution drops, right, as you increase the radius. So the resolution is the smallest distance. So if you calculate the horizontal motion over here, right, and over here like that, as you increase the radius, the horizontal motion in millimeters or sub-millimeters is increasing. Okay, so which means the resolution decreases. Then when you come to spherical robot, they both decrease radially because when you have the rotary joints, what you can control is the smallest angle. So when you convert the angle into distance, right, as you move away from the robot, from the center, you're going to get higher distances. Okay, so that is why the resolution decreases radially. SCARA, there you can see very complicated. You can't say anything for sure for horizontal resolution, but vertical resolution is uniform because in case of SCARA, you have both first and second axis vertical, right? Vertical. So therefore, vertical resolution is uniform. It's not going to change. They are going up and down, right? So that is for the last joint, right? That is a vertical motion. Other two joints are vertical axis. So they are not going to contribute to vertical motion. The only actuator that contributes to vertical motion is the third joint. So that is a uniform resolution. All right. And finally, the articulated arm is again very complicated. It's difficult to say anything with certainty unless you have complete workspace analysis done, right? So complicated, so they vary. Now here in this illustration, you can see again something very important for positioning machines like manipulators, the accuracy and resolution. Accuracy and resolution. Now, let's say this is your end effector, right? In two consecutive positions.
Excuse sir.
Yes.
The effector means the final final length or final point of the robot.
Say it again.
Sir, what you meant by the end effector?
End effector is the tool that is attached to the manipulator. Okay. So if you have a welding manipulator, the end effector is the welding torch, the tool the robot is carrying. It can be a gripper, can be a laser cutter, it can be welding torch, it can be anything, the tool. Okay.
Okay, yeah, sir. Thank you.
So let's say you are doing laser cutting using a manipulator, right? So this is the tip of the laser beam, right? This is where you get the laser beam, and you use it to cut material. This is the cutting point, actually, right? So when you move the position, right, you keep giving commands. So between two commands, two consecutive commands, right? These are the positions, let's say, right? This is an illustration. What you see here is two adjacent positions of the end effector. You can't have these two positions any closer than this, because the end effector assumes this position, and after that you give the smallest command, smallest change in the command, and the manipulator comes to this point. So there's no way manipulator to stop anywhere in between, because what you have given, the control signal that you have given is the smallest deviation, smallest control signal. For that, the robot moves over here. Okay. So now let's say your target point is here. Your target point is here. You want the manipulator, you want the end effector to be located here. If it's a laser cutting thing, you know where you want to cut it, right? So this is the target point. You want to go over here and cut. Then your control system drives the end effector as close as possible. Of course, you don't get the perfect positioning. Let's say the robot end effector stops over here. It doesn't go to this point, but stops over here. So there you can see this is the final point of the end effector, actual final point of the end effector, and this is the target point, and the difference is error or accuracy. So everybody knows that, right? Now, let's say you are not happy about this accuracy because you couldn't get the manipulator to the target point. So what you do is you give the smallest incremental command to the manipulator. Okay. And as a result of that, the end effector moves over here and locate its position here. So it doesn't go to the target point, but somewhere over here. Because this is the smallest distance that the manipulator can position itself next to each other. So this smallest distance is what is called the resolution. Okay. So I really wanted to explain you the difference between accuracy and resolution. Right? Any questions about that? All right. So as technical people, I think these things you need to remember, right? Because those things are very kind of fundamentals for technical people. Now, other than the manipulators, robot manipulators, there are structures, mechanisms like this, for example, parallel linkages. Remember, I was using a word earlier like serial manipulators. Serial means one after the other, right? Like a series. In other words, it has a starting end and ending point, right? Start and end. These mechanisms, they are not serial links, but parallel linkages. Parallel linkages. There you have number of links like that, right? And they are connected. Once you, let's say you have this one and this one, you have full freedom. And let's say you have this one and that one, again you have the full freedom to move. But the moment you attach them together, then you are seriously constraining the motion. Okay. And sometimes you get additional advantages, right, by restricting the motion. And when you close the loop by connecting these links, right, you are not able to control these joints independently, right? So, for example, you can have these three joints, like passive joints. They are free to move, right? But you don't have any actuators there, right? Whereas this joint and this joint 1 and joint 3, you can control using motors, right? Their position. So when you control these two joints, these three joints will assume whatever angles they are supposed to have, right, in order to maintain the constraint structure of the parallel linkage. So there is a very popular parallel linkage mechanism called Stewart mechanism or Stewart platform. So let me show you this Stewart platform. Oops. So let me Let me get it from my folder. Stored platform. So this is the stored platform. So if you notice it very closely, you can see these joints, right? They are like universal joints, right? They have more than 1 degree of freedom. And these mechanisms, right, can actually handle huge loads. Oops. Right. So you use these platforms in order to handle huge loads. You can see these 6 linear actuators. Linear actuators can handle huge loads. So if you have 6 of them together, they can handle very big loads. Okay. But they cannot move fast, right? They move inherently slowly. So if you have some very heavy item and you want to control the direction or orientation, right, very slowly, the ideal platform is stored platform. And you can see antenna tracking systems, right, is one of the most appropriate application for stored platforms, where you have a huge antenna, very big, very heavy, right? But you don't want to rotate it very, very quickly, right? Because you're trying to uh, uh, direct the antenna to a certain satellite or something, right? So, and that is not going to change very quickly. So your movements are very, very small. So the ideal platform is Stuart. So now I want to tell you a few terms that we use in robotics. Degrees of freedom. When you purchase a manipulator, this is the first thing. How many degrees of freedom that you require, right? So the definition of degrees of freedom is the number of independent position variables. When I say position, it doesn't necessarily mean distance, right? It can be angle as well. So distance or angle, both, right? We don't see any differentiation, any different words for distance and angle in robotics, right? So we call it position variables or joint variables. When I say joint variables, some joints are prismatic, so the variable is distance. Some joints are rotary, so the joint variable is an angle, right? Whatever it is. So the number of independent position variables that would have to be specified in order to locate all parts of the mechanism. So let's say you have a manipulator. You want to calculate the endpoint of the manipulator, right? You draw the structure and you figure out how many variables are there in the manipulator. And if you do not know any of these variables, you cannot calculate the endpoint. Okay. So the number of these variables is called degrees of freedom. Usually in articulated manipulators that you have seen, number of videos, right? So they have either 5 or 6 joints, 5 or 6 degrees of freedom. So usually one joint means 1 degree freedom. One joint is 1 degree of freedom. But sometimes you can see some joints have more than 1 degree of freedom. So degree of freedom is variable. Okay. If you have joint means a physical joint, right? You can have a physical joint, but mathematically more than one variable in that same location. So then it is a multi-degree of freedom joint. Now this is a good time to discuss about human hand, right? The arm from the shoulder to the wrist. That is a very good example of mechanical manipulation, right? Human hand, the arm rather. So if you look at the shoulder joint and then the elbow and the wrist, right? The human upper arm, right, is actually three-link manipulator. Three-link manipulator. Okay. So the first link is actually the upper torso. Second link is the upper arm. Third link is the forearm, like that, right? So after the forearm, it is the end effector, which is the hand, Okay, so you have the upper torso, forearm, upper arm, and then the forearm, and then the hand, right? So if you take the hand out, right, that is the end effector, you have a three-link manipulator kind of thing, three links. In that case, the first link is the upper torso, which is, let's say, 0, right? And then it is stationary, it doesn't move, so other joints move. So if you look at the shoulder joint, how many degrees of freedoms are there? Shoulder joint. How many different ways you can move your shoulder joint? So that every independent motion is a degree of freedom, is a variable. How many in the shoulder joint? Any ideas? You can test it yourself if you want, right? Can you rotate your arm around a vertical axis? Vertical axis parallel to your body. Can you do that? So can you rotate your hand like that? Yes or no? Are you guys there?
Yes, sir.
Then can you rotate your hand arm like that? Yes or no?
Yes.
Yes. So this is theta 1. This is theta 2. And if you stretch your arm like that, so this is your arm, right? This is the upper torso. You can rotate it like that. Twist. It's a twist. It's not the complete rotation like this. It is a twist. Right? So you have 3 degrees of freedom. You have 3 degrees of freedom in your shoulder. And then look at your elbow joint, right? How many degrees of freedoms are there?
One.
There's obvious one is there, right? This is your elbow joint, right? Your hand, like that. So this angle is one joint, right? Theta 4. But there is another joint. There's another joint. If you look at this axis here, right? You can actually twist it like that. You can do that. The forearm you can rotate around the axis of the arm itself. Right? You can twist it like that, rotate it. So this is theta 5. And then you go to the right. You go to the wrist. This is your hand, like that, right? You are here. There you can actually if I draw this axis here, right? You can rotate it like that. Okay. So from your wrist, you can have this rotary motion. So that is theta 6. Theta 6. But not only that, if you look at this parallel axis here, right? This axis here, into the board, right? Into the plane. Around that, you can move it a little bit this way. You can move it a little bit that way, not too much, right? This is theta 7. Okay. In two different orthogonal directions, you can have two angles. So altogether, 7 angles. You can change these angles independently, right? So the human upper arm, right, is a 7-degree of freedom manipulator. 7 degrees of freedom. So that is very important. 7 degrees of freedom. Now, put it aside and think about in general manipulation, right? Handling objects and so on, right? You want to control your hand position, right? And also orientation. When you grip objects, when you write, when you handle tools, when you drive, when you open a door, right? When you carry a bag, you want to control the orientation of your hand. And also you want to control the position of your hand. So if you look at the position is given by, let's say, if you stick to Cartesian coordinate frame, it is XYZ. And if you define your position in a different coordinate frame, spherical or cylindrical, you have still 3 coordinates, right? So in order to control your position, you need to have 3 coordinates independent to each other. So you can have 3 of these angles, right? You have 7 angles. 3 of them you can use in general, right, to control this position. So once you control the position, now you have to control the orientation, right? Because if you want to write on paper, not only the positioning, but also the orientation control matters, right? So when you control the orientation, now you need 3 more variables to control the orientation in the right way. So therefore, you're going to need altogether 6 degrees of freedom. Okay, if you want to have the full controllability of position and orientation in your workspace, right? So any manipulator which is having 6 degrees of freedom, right, can control the position and orientation arbitrarily. Arbitrarily means any, right? If you do not have 6 degrees of freedom, right? If you have, let's say, 5 or 4 or 3, right? You can control position, but not the orientation. Or maybe you can control the position to some extent and orientation also to some extent, but you do not have the perfect position and perfect orientation control. So some performance is actually not there if you do not have 6 degrees of freedom. Okay. Now, if you look at the human hand, right, the human arm rather, you have more than what you need. You need 6, minimally 6 to control the position and orientation arbitrarily, but now you have 1 in addition to that, 7. So, what is the advantage of having more than what you really require? You need 6, but you have 7. Can somebody tell me what additional advantage is there for humans, right? Because they have 7 degrees of freedom in their arm, whereas you need only 6 to control the orientation and position arbitrarily. Any thoughts? No idea? So the advantage is redundancy. Just one word, redundancy. Human arm is a redundant manipulator, which means it has more than one configuration in the arm in order to reach same position and same orientation. Multiple solutions, in other words. Okay, so the arm configuration is another word you need to remember. The configuration. Configuration is the angle set. What is the first angle? What is the second angle? What is the third angle? Fourth, and so on. Right, and then you get to the final position and orientation. Now, in case of redundant manipulators, you have different angle sets. Different angle sets in order to reach the same position and orientation. So if one configuration is not possible for whatever reason, you always can revert to other configurations in order to reach the same position and orientation. Okay. So that is the advantage of having more than what is really required, right? As a non-redundant manipulator. Okay, so there are some some redundant manipulators that is more than 6 degrees of freedom. Like there are 7 degree of freedom manipulators or 10 degree of freedom manipulators. When you have more joints, right, the manipulator becomes like a snake. Okay, so it can actually change the configuration quite a lot in order to exercise various movements, right? Right. Now I want to show you the manipulator control system, right? In any robot manipulator, right? it has these components in the system, right? In fact, this is what I used for my PhD to test various control algorithms, trajectory planning, and so on. So you can see the manipulator over here. This is in fact a 5-degree of freedom manipulator. You can see joint 1, joint 2, joint 3, joint 4, and joint 5. You can see the 5 joints, right? So pretty easy to figure it out in this configuration. So theta 1, theta 2, theta 3, theta 4, and theta 5. 5 degrees of freedom. It's not a redundant manipulator. And some applications are we call symmetric tool applications. Like in industry, there are a lot of applications where you don't really need 6 degrees of freedom. Like for example, when you write using a pen, or when you write using a whiteboard marker, do you really rotate the marker to a certain angle and write? Or when you hold the pen, is there a direction you need to hold the pen? No, like a ballpoint, any direction will write, okay? There's no particular direction that you need to hold the pen, right? Whatever rotation, whatever orientation is okay. Orientation in the sense along the same axis of the pen, you don't need to control the angle, like, right? So therefore, you don't worry about that degree of freedom. So you can get 1 degree of freedom out of the requirement. So the 6 becomes 5. So those applications, like for example, a laser cutter. So when you use a laser cutter, it's a beam. Beam, you need to orient it in a certain direction, but there's no rotation, right? An angular orientation of the beam, like a pen, right? So if you look at a gripper, it's not like that. Gripper you need to control the rotation before you grip. But if it's a welding torch, any direction you can use because it's a symmetric tool application, okay? So therefore, there are a lot of robots where the number of degrees of freedom is 5, not 6. So this is one of them. So you can see the servo controller here. You can see the safety switches. You can see the feedback, and you can see the reference input generator. So these are the blocks. These are the items in a robot manipulator system. So let us see how it works. Now, in the reference input generator, right, you create the motion trajectory for the manipulator. Let's say if it is a 1 minute operation, say it's a 1 minute operation, okay? So you break down 1 minute into 10 millisecond samples, right? 10 millisecond samples. So 10 milliseconds means you have 100 samples, right, in 1 second. You have 100 samples in 1 second, and you have 6,000 samples in 1 minute. Okay, 6,000 samples in 1 minute. So in these 6,000 samples, starting from 0 up to 1 minute, you are going to specify the angle for theta 1, theta 2, theta 3, theta 4, theta 5. Okay. What is theta 1? What is theta 2, theta 3, theta 4, theta 5 at time 0? And after 10 milliseconds, what is theta 1, theta 2, theta 3, theta 4, theta 5. After 20 milliseconds, what is theta 1, theta 2, like that. This is what is called the desired trajectory. Desired trajectory. Whether the robot is going through that trajectory or not is a separate issue, right? But when you plan your trajectory, you plan it like that. Okay. So then what you do is you send this file, right, like a file input, right, to the servo controller, line by line, line by line. The first line, time 0, the second line, 10 milliseconds, third line, 20 milliseconds, like that. You send it according to the timer, okay? So once you send the first line, the servo controller latches these positions, theta 1, theta 2, theta 3, all references. Now this is a control system problem, right? The servo controller has 5 servo drives here, from here to here. These are actually the 2 handles of a door. You can actually hold these 2 handles by hand and pull it out. When you do that, you can see what is inside. It is identical 6 servo drives, 6 packs. So everyone gets a reference from the reference input generator. And it's a feedback loop. And in the feedback loop, you know there's a reference. And this is the reference, the first one, the reference is the reference angle for joint 1. And it keep it there for 10 milliseconds. So when the 10 milliseconds elapsed, it gets the second reference angle from the reference input generator. Okay, so that is how it goes. So after that, what happens is that the servo controller reads joint 1 angle, the present angle, existing angle, through the feedback. You can see the feedback, right, coming from the joint encoders, theta 1. The servo controller reads what is the angle for theta 1 now. Then servo controller knows the error, the difference between reference and actual. That is the error. And there is a particular compensator, the control system, right? And it will eventually drive the servo motor in a suitable manner so that theta 1 actual angle, right, goes to the desired angle. And it has 10 milliseconds to do that. 10 milliseconds. Okay, so therefore now you can track this feedback, theta 1 actual position coming from this switch box to the servo controller, and then the servo controller calculate what is the required actuator command or control signal, and it sends the control signal through these wires, right, through these cables to this switch box, and then to the actuators, that is the motors here. That is how it happens. So this loop operates, right, from the joint encoders through the feedback to the servo controller, and then to the control input back to the actuator. So this loop takes place many times within 10 milliseconds, right? This is a very, very fast control loop. And after 10 milliseconds, theta 1 has reached probably the theta 1 reference. And at that time, the reference input generator gives a new reference command. Now you go here, now you go here, now you go here, like that. Gradually, the reference input generator gives set the reference, right, for the servo controller to follow. So we have done control system design, simulation. So therefore, I think it's easy for you to understand what's happening. And also, this is a research manipulator, right? Not an industrial manipulator. That is why we have complete access to anything over here, right? You can access the server boards, you can access the joints, etc. In industrial setups, if you go and see the manipulators, you don't have that kind of access, right? Access is not given, because when you are given access, you are inviting for problems, right? When we do research, we always deal with problems. So therefore, it's okay, right, to have the architecture open. So whenever you do this kind of research, sometimes things go wrong, right? Sometimes things go wrong, and your trajectory planning algorithm or your controller is it doesn't work the way you expect it to, right? Sometimes serious vibrations happen, right? Sometimes joints stop moving at all, right? Like that. So in such situations, you have access to these safety switches. Whenever you operate the robot, before you send the command to start the operation, right? You need to have your fingers on these switches, right? Just in case if you see any bad noise or any vibration, you need to turn off these switches. The moment you do that, these control signals will not go to the actuator and the robot will freeze. Okay. So that is how it happens. And in industrial manipulators also, when you do that, you have what's called the deadman switch. The moment you release it, the robot stops, freezes. Those are the safety features. So that is how a manipulator operates. Right. So now let me show you this block diagram, right, which explains you a bit more into the control loop, right? So we have the trajectory planner or the reference input generator and the servo controller and the robot, right? These are the three pieces, right? Um, so this is how uh, the whole system operates. Again, as I explained, the reference input generator generates sometimes position and also velocity together, right? And then it can actually give the velocity input or the position input, right, to the controller. And the controller runs various control algorithms. It can be PID, it can be computed torque control, it can be a fuzzy controller, right? There are various different controllers, whatever the controller may be. So there is a controller which will generate the UK, the control signal, right? And it goes to the robot arm and joint by joint, right? Individual joints. So each joint will undergo some change in position and velocity. So then through the feedback loop, the servo controller knows what is the new position, right? As a result of the control signal. So when this is happening, there's some process that is on the watch, right? Tracking performance evaluation. So as I mentioned earlier, the trajectory that you generate here is what is called the reference trajectory. It is the desired trajectory, right? And very much like when you send a spacecraft, right, from Earth to the Mars, right? You have a trajectory. You have a time trajectory at every step of the way, every hour. The spacecraft has to be in this position with this orientation, this position with this orientation, like that. You plan the whole trajectory, then that's how you say in advance, okay, this particular spacecraft is going to land on the Mars or the moon on this particular day and this particular moment, time to the minute. They tell you, right? So because they have the trajectory planned already. And after that, you have the control system, actuators, thrusters to make sure that you do not let any error to propagate during the whole period, right? So when the spacecraft is flying, it doesn't go exactly on the trajectory that was planned. There are deviations, okay? There are deviations. Sometimes it goes beyond what it is supposed to go, and sometimes fall short, right? But these errors are corrected on the way, so that finally it goes to the destination with a little error, not much, okay? So this is happening in every uh, uh, planned trajectories, planned operations in robotics, mechatronics, space flight, etc., etc. So uh, how close is your servo controller following, right, the desired trajectory is to be evaluated, right? So some sort of evaluation is required. You put on the same timeline the desired trajectory and the actual trajectory. Desired and actual, right? So if you see a major difference between the two, probably you want to change the control algorithm, okay? You have to figure it out, what causes this difference, right? So after a while, after doing modifications, gain tuning or controller modification, you want to get it to work, which means you have the desired trajectory, you have the actual trajectory, and they're closely apart, right? Closely apart. So that is how it works. Any questions? So here, this is the control loop description. I have already explained to you everything. I just want to mention about the dynamic model here, right? Dynamic model. These are the models that we worked on in the first couple of semesters, right? Um, Plant dynamics, open loop plant model, feedback models, etc., right? For manipulators also, you can have a model, a second order model, simple model, okay? And using that model, you have to have the control loop, right? What sort of control you want to have? Is it a PID or state space model, a controller or whatever, right? Or observer base. So that is entirely a different topic. And what are the errors when you operate a feedback loop like that, right? This is a huge undertaking because you have to follow a trajectory, because this is not a stabilization problem like in air conditioner or a boiler, right, where you need to maintain the same level all the time. When you set the temperature to say 25, 27, whatever, you're not going to change it very often, right? You keep it there for a while. Boilers are also like that. You want to maintain the pressure at a certain level. Then the water level controls maintain the level, and you are not going to change it very often. But this is a servo problem where it is bound to change. Every 10 millisecond reference is going to change. Okay. So it is a tracking problem. It's a tracking problem. So therefore, it's much more serious than the regulatory problem, right? So therefore, there are a lot of errors that you can expect here. What are those errors? Namely, actuator saturation. Because if the controller fails to achieve the reference point, say within the control horizon, that is about 10 milliseconds in previous example, by the time the servo controller receives the next reference command, it's already falling short. So now it has to cover even more angle than what it was supposed to do in the previous 10 millisecond time. So gradually, the servo controller gets an increasing demand right? An increasing demand to drive the joint 1 or 2 or 3, whatever, within 10 milliseconds, and the actuator tries its best, and within 10 millisecond, it cannot actually cover that angle. So it goes to what is called the actuator saturation. So if it happens, you will see one or more, right, joints saturate, which means they are operating at the maximum torque level, but yet they can't actually cope up with the reference signal, right? So that is what is called the actuator saturation. If it happens, your actual trajectory will deviate from the reference trajectory. So you might ask, so why is it in the first place that somebody would plan a trajectory like that? That is a very valid comment. Usually when you plan trajectories for manipulators, you need to know the capability of the actuators, right? What is the motor, right, attached to joint 1? What is the motor attached to joint 2? What are their capabilities? How much they can turn in 1 second or 100 milliseconds? And you should not ask, you should not make your trajectory, right, which asks the servo controller to rotate that joint beyond what is maximally possible, right? So that is why these trajectory planning algorithms are supposed to do. They should not plan any incremental change, right, which is more than what the actuators can perform, right? And if you do that, you will lead to actuator saturation. And also there are backlash errors. Backlash means, let's say you keep turning joint 1 in clockwise direction, and at a certain point, you want to turn it the other way. So the moment you want to do that, the joint, the geared joint, right, the actuator turns the opposite direction, change the direction. But because of the backlash, the actual joint does not move for a while. And after a little while, maybe 3-4 milliseconds later, it will start turning. So therefore, that will cause temporary errors in the trajectory. And also gravity, as I explained to you previously, all the joints, horizontal axis joints, will have to cope up with the nonlinear gravity problems. So that can cause additional torque requirements, and it might lead to actuator saturation also, right? Certain things can be foreseen, right, before you actually implement it, whether the nonlinear gravitational components cause any additional torques, which leads to actuator saturation, right? You can simulate that and see for yourself before you actually implement your trajectories. And also friction. We don't know how much the friction is, how much of a torque of the actuator is taken just to compensate for friction. And you assume that the joint 3, let's say, produce 300 Newton meter torque, and you expect that torque to be utilized for the motion, initial motion, only to find out, okay, 1/3 of that is actually used to overcome friction. Okay, so you don't get the full torque for the motion. So therefore, you don't get the full acceleration, velocity, and position, right? So now you can understand, if you go to the details, this is very complicated, right? And gravity, nonlinear gravitational forces, gravitational torques, friction is not easy to accurately model and include in your simulation, right? And backlash also, right? We don't know for sure how much is the backlash. And using sensors, you can measure on the fly. In that case, actuators become very expensive. So when you put all these things together, it becomes a bit complicated. Therefore, how the industry works is that you leave very big torque margin to counter for friction, gravity, backlash, everything, right? And if you know that the robot, the joint needs, let's say 300 Newton meter, you oversize the actuators to have 500 Newton meter so that it never goes to saturation. So that is a very easy way to tackle the problem, but additional excess stock margin, right? And the robot becomes a bit expensive because the actuator is oversized, but it will not have other problems, right? So therefore, the motors, when you run, they are not actually running with their actual capacity, right? They are not using their full torque capacity when you're running. And also, there are simulators. When you purchase a manipulator from a reputed manufacturer, you always get what is called a simulator. So you can plan your trajectory and put it to the simulator and see for yourself whether the robot is moving as you wish, right? And the simulator, depending on how sophisticated, how advanced that is, will show you some of the errors that you would encounter if you practically implement that, right? In that case, you can adjust your trajectories, right, until you see no problems in your simulation. And at that point, you can bring it to the manipulator and feed it to the servo controller and actually implement this control operation, right? So that's how it happens, right? Let's take a little break right now, right? And I'll start from there after about 10 minutes. Yes, go ahead.
Where can we download the lecture notes?
I will place them on the Moodle. When I upload it to the Moodle, you will get a notification so that you can download, right?
Okay, okay. Thank you.
Okay. Right. Now let's look at the design approaches. So here you assume yourself as a manufacturer of robot manipulators, right? So how do you decide what you want to do, right? So this is another fantastic way of studying the subject, right? Now, as a manufacturer, as a designer, these are the things you need to look at very seriously and make decisions, right? The first one is mechanical and control attributes. So what is that? The size of the manipulator, because you know there are small manipulators, there are big manipulators, right? What is the size that you want? Because you are targeting a certain one or few applications, right? It can be welding, it can be part mating, it can be laser cutting, buffering, etc. So depending on that application, right, you need to decide the size of the manipulator and the speed. Again, there are slow manipulators, fast manipulators. What is sort of speed you need to have? Loading and unloading capability. If you are handling material, you need to know up to how many kilograms, right, you can handle. Then comes number of joints, whether you want to have a 3 degree of freedom manipulator, or as I explained, whether you want to have 5 degrees of freedom manipulator for symmetric tool application. So whether you need to have full freedom, that is for position and orientation to be specified independently, that is you're going to need 6 degrees of freedom, whether you want to have a manipulator like that. And then there are geometric arrangements. Okay, you know how many degrees of freedom you need, but are they rotary? How many of them are rotary? How many prismatic? And what is the sequence? Which ones are rotary? Which ones are prismatic? Okay. And then finally, something new to you, that is stiffness and compliance. That is pretty advanced stuff. Stiffness and control compliance, that most of the industrial manipulators are very, very stiff, which means no compliance. But nowadays there are manipulators like, for example, universal arm. They have this compliance to some extent, which means if they hit on something, they will temporarily forget the task, but try to accommodate that force, which means if there's any undue or unexpected force, robot needs to stop, freeze, or slow down, right? But most of the industrial manipulators to date are not like that. They are completely blind to that kind of scenarios. They do not expect any obstacle to be around them, right? Because they're blind, they're operating as they're instructed to do, right? And they're very stiff. Stiff means accuracy. Stiffness means accuracy, right? They want to have full throttle, full power in order to eliminate any of the errors on the fly, which means they're very stiff. They want to hold the position very closely to the desired position. So if there's a small change, they want to come back to the desired position, right? Very quickly. So they're very stiff. So as long as there are no obstacles around, there are no people around, you can have very high stiff manipulator, so that your welding operation, your laser cutting operation will be very accurate, because you want to cut, if you do laser cutting, very straight lines, very accurate positioning, right? And if you want to do welding also, you want to follow the line very precisely, as precise as possible. And also, if there's any deviation, quickly recover from that error, right? So you got to have this high stiffness. But on a bad day, on a very unlucky day, this might hit some person and seriously damaging the person, because robot doesn't know whether there's a person. He's not supposed to be there, right? And also, if you look at advanced applications where robots are to work with humans together side by side, not like the welding robot, laser cutting robots, right? Maybe in the future, they will work together with humans, right? In that case, you cannot have this stiffness at all times, right? Sometimes there are cases you need to have high stiffness at a risk, but other times when they work with humans, they need to have compliance. So you accommodate the external forces, and temporarily you accommodate errors, right, in order to minimize the contact force. When the robot is in contact with something, there's a force, contact force, and if that force is too much, you have to reduce that contact force. One way to reduce the contact force is to deviate from the trajectory. Okay, you have a desired trajectory, and when you try to go through that trajectory, there is an undue force, unexpected force, and to reduce that force, you deviate from the trajectory. So it is a trade-off between compliance and stiffness. Okay. So whether you want to have that in your design, you have to decide consciously. Okay. So then when it comes to number of degrees of freedom, what are the options available? So the more joints means what? More dexterous, right? But if you really need that sort of dexterity in your manipulator, you have to decide, right? And if you have more degrees of freedom, more joints, which means it's going to be too expensive, right? Whether it is affordable or not. So therefore, a lot of people, what they do is they customize their manipulators rather than generalizing manipulators, okay? There's an optimum point where you can place your design, leaving some space for general applications, but at the same time, you customize it to a certain few applications, right? So what I mean by specialized design is you design a robot just for a specific application. So which means you can't use the same robot for a different application, okay? You need to change quite a lot if you have to. Then general design means it's a very generic robot manipulator, and you can customize it to various applications, at least few applications, right? So in order for you to be able to deploy the robot for a number of applications, right? Uh, you need to have that general capability in your robot manipulator. So which means you need to have more capability than what any of these individual applications really need. Okay, so let's say there is a certain application where you need 3 degrees of freedom, all rotary, and there's another application where you need 3 degrees of freedom with 2 rotary and 1 prismatic. So if you want to design a robot to be able to handle both of these, maybe you need to go for a 4 degrees of freedom manipulator with 3 rotary and 1 prismatic, like that. So your specification um, increases a bit, but the advantage is that now you can use this manipulator for 2 applications, right? Now finally we come to the sensors. Now when you purchase a robot, you don't purchase sensors. So there are 2 different types of sensors. One is the sensors inherent to the manipulator, because you can't use the manipulator without the internal sensors. For example, the joint encoders. How can you control a feedback loop, right, around the manipulator if you don't have the joint encoders? So therefore, joint encoders are actually inherent part of the robot, and those are sensors. But usually when we don't refer to those joint encoders as sensors here, what we really refer to as sensors here is the application dependent sensors. What sort of sensors you need for your applications? Like, for example, if you handle objects, you need to have tactile force pressure sensors. If you want to use this robot manipulator for some sort of vision based applications, you need to have cameras, vision systems, okay, like that. So they are not part of the manipulator, and also not part of the manipulator is the end effector. End effector is not part of the manipulator. It doesn't come, right? Sometimes the same manufacturer might have a number of end effectors, but generally they're separate. They're sold separately. So you have to purchase end effector and whatever additional sensors you need, right? So that's what it is, right? The robot manufacturers, this is how they do. Now, we also need to know what is called the constraint motion or constraint environment. This particular figure shows you constraint environment where you can see a robot manipulator. This is what is called the Puma or Puma. If you go to the internet and type Puma 560 or Puma 720, you can see these manipulators, right? I think this is coming from Stanford. They are in 80s and 90s. They did a lot of robotics projects. Oh, no, this is Steamland Robotics Institute, Carnegie Mellon. This is where this project is happening, the space tech robotics project. I'm part of where we try to use space manipulator um, to refuel geostationary satellites and keep them going for um, beyond their lifetime, right? To increase the lifetime by 30–40%. So this is coming from CMU. So you can see the mobile platform here. On top of that, you have the manipulator. So this is a mobile manipulator. And it takes this paint bucket from a rack, and there's the whole sort of bricks here on the ground. It's constrained area, so you can't go there. It has to move, push back in this pose, and come over here, right, and then turn back, and then go under the ladder to some other place. And so this is constrained environment, right? And robot is actually handling something. So there's a force application, right? So this is what is called a constraint motion. You don't have the full freedom to design your trajectories, right? So if you look at other typical applications where you can deploy robots, like for example, window washing. Think about very tall buildings, skyscrapers, right? You get dust gathered on the windows, right? And you want to wash it. Otherwise, it looks pretty bad, right? After a few months. How do they do that? They have this gondola kind of thing, and there are people, very risky operation. They wash it manually, just like they wash uh, any building on the ground, right? But you can use robots for that. All what you need to do is have a robot and program it to wash the windows where you need to apply a certain force against the window and then move up and down or left and right, right? So it's a force control application and also motion control application, right? You need to maintain a certain pressure against the wall. Otherwise, you are not washing it, right? You are just moving, but you are not cleaning the dust, right? So applying a force normal to the window and moving parallel to the window. The force control and the motion are orthogonal to each other, right? So this is a constraint motion application. And what about robotic surgery? In surgery, the robot arm gets in contact with human tissues, right? So can you apply additional force or excess force on a human tissue? No, you have to maintain all the forces below a certain limit, depending on the organ you're handling, right? And also polishing. There also you need to maintain a certain force against the object, and then you perform the motion, right? So as you understood probably in case of window washing, the force axis and the motion axis are normal to each other. So therefore we know force and position control is generally complementary. Okay. So we have this hybrid control thing. Force and motion control are implemented along orthogonal directions, right? So this is kind of advanced stuff. We are not going to deal with constraint motion in this module, but we will do some sort of force propagation along the manipulator, right? If you have to exert a certain force here, right? You need to generate this force at this point by controlling the torques along the arm, right? Joint 1, joint 2, joint 3, like that. All these joints will have to generate some torques, right? In order to generate this lifting force here at the end. So we will do this analysis up to that point. Now let me show you this little video on manipulator programming. Now present day manipulator programming. Okay, by the way, manipulator programming is teaching the manipulator what to do and how to do. Right? If you have, let's say, laser cutting operation, you saw the video, right? The robot is following a straight line, actually piecewise linear trajectory, right? Sometimes there are curves, but if you just forget about the curves, the robot moves through a set of straight lines, A to B, B to C, C to D, D to E, like that. How do you program this entire trajectory? Do you want to mathematically model it and feed it? And whether that kind of method is acceptable to the industry, the engineers or technical people, they'll have to sit in front of the computer, plan the trajectory, and then upload it. It'll work. That's not going to be the way it is. You need to have much more practical approach in the industry. So therefore, the manufacturers design this unit, which is called the teach pendant. Teach pendant. Using this teach pendant, anybody with a little knowledge about the manipulator can program a manipulator. Okay. So this teach pendant lets you select any of the joints. Now here you can see 1, 2, 3, 4, 5, 6 set of switches, right? The 6 means 6 joints. This particular manipulator, Denso manipulator, it's a 6 degree of freedom manipulator, 6 link manipulator. So you can select any of the links and control the position using this lineup of sensors, right? This is the joint control. Individually, you control the joints, right? So let me show you this video.
Hi, I'm Brian with Access New England. Today we'll be exploring how to jog and teach.
I don't think you hear the sound, so therefore let me stop sharing and come back.
Hi, I'm Brian with Access New England. Today we'll be exploring how to jog and teach points with a. Okay, so we'll be using a 6-axis robot for this demonstration. To begin, you'll need to check to make sure that the key to the teach pendant is set to manual mode. Then you'll need to grip the dead man switch and press the motor button. The dead man switch needs to stay depressed. Once the motors are engaged, the LED will light up. The next thing to do is to check the mode that we are in by pressing the mode button on the top of the teach pendant. We will switch the mode from XY to joint. It is important to check your speed before making any manual motion with the robot. Typically you should start with 10 to 20%, but since I know I have enough clearance, I will use 50%. By pushing the J1 plus or minus buttons, we can jog the J1 axis in the positive or negative direction. We can do the same with J2, and J3.
So can you see that you can select the particular joint you want to move, J1, J2, J3, and then move it plus and minus directions, right? And when you do that, there's a particular speed you have already set. If you want to change the speed, you can do that, 50%, 100%, like that, right? whatever speed you have selected would be the default speed. So
J4,
that is fourth axis, that is fifth axis,
J5,
and that is the last.
and lastly J6, which is the rotary motor on the end effector.
It's rotary motion. Right? So the last axis, sixth one, is where the symmetric tool application comes from. If you do not need that rotation, you don't need that degree of freedom. Okay. So if you are operating with a, so let me pedal back and show it again. So look at this last joint rotation, this rotation, right?
If we select the motor,
This one,
which is the rotary motor on the end effector,
right? So that motion is not required if you do laser cutting, welding like that. Okay. And if you have a robot to write on the board, again, you don't need that rotation.
if we select the mode button again, we can change from joint to XY coordinates.
Right. Now this time, this mode of operation is XY operation. Earlier it was joint mode. Individual joints are being moved, right? You can select joint 1, 2, 3, 4, 5. So then only that joint moves. But you have no idea where the endpoint is going, right? When you do that. But now it is XY mode. So in case of XY mode, you are giving the commands to the endpoint to move forward, backward, left, right, up, down, like that. It is the Cartesian space command. In order for this command to be executed, the controller has to control all these joints, right? Combine the individual motions of these joints in order to move this point linearly in the workspace, right? So that is a complete coordinate transformation, right? There are a lot of calculations that you have to do in order to move this endpoint from here to here along the x-axis, assuming this is the x-axis. How you have to control the joint angles, right? That is what is called inverse kinematics. Inverse kinematics is a complicated mathematical process. You need to solve inverse kinematics, right, in order to calculate the joint angles, right, for a particular end effector position and orientation. Okay.
This allows us to move along the x-axis.
I think you saw that, right? The motion, all the joints are moving and the end effector moves along a straight line.
Along the y-axis, positive or negative, and we can also move up and down on the z-axis. Additionally, we can rotate about the x-axis, rotate about the y-axis, or rotate about the z-axis. Next, what we will need to do is use what we've learned to jog the robot arm into the position and
Right. Now, you have seen jog motion, which is individual joint motion, and also XY, Cartesian motion, okay? And you know the difference clearly. In the first case, jog motion, only one joint at a time, and you have no idea where the endpoint is moving. The second one is much more intuitive, and all the real world applications, that is exactly what we need. So we need the robot arm, the end effector, to move along with respect to a certain path that we define in the workspace, XYZ space, okay? Now the next thing is that you want to give a set of points for the manipulator to move through. The first point, the second point, third point, fourth point, and so on. Okay, so if you want to do this in a computer, you need to recreate the whole thing in the workspace. Okay, But rather than you do that, you can program the robot as you're about to see here.
And posture that we would like to teach as our first point. As a goal, we will try to bring the end effector near to the shaft of the gearhead.
This is the first point. You have a little hard time to move it there. You can use either of these modes, jog mode or XY mode, right? It's a bit difficult, but eventually you can bring the manipulator with the right position and orientation, right? Position and orientation into the first point. Right?
We'll stop at this point. And
I think you saw that. Now you have the position and also the orientation. You are happy about it. Then you enter to the teach pendant. This is my first point. Okay, this is my first point. Then what does the controller do? It will take all the joint positions right now, right? Every joint has a 0 position and the end position, right? So within that dynamic range, you are at a certain point. So the controller will memorize those joint coordinates for all 6 joints, right? And that is your first point.
select the speed button again to change to a slower speed, 10% or less when moving close to other objects, so that we can avoid collisions.
So they are actually still, we have not achieved the final, the first point. We have come very close to the first point, and then he reduces the speed so that he wants to get a very fine motion to get to the first point, right?
Now that we're at our location, in order to teach the point, we'll hit Program, var, then Position, and scroll up to P0. If we hit Get Position, the controller will record the current position and posture into the P variable we've selected. We can then teach our next position, which we will store into variable P1. We can use the same method as before, except this time we will select P1 instead of P0.
Okay. Now he moves the manipulator again to jog mode or XY mode to the second point.
Once again, after selecting the position variable type, we'll select P1, hit Get Position, and record it into the P variable. If we want to test out our move path, we can hit Move within the position variable screen. If we hold OK, the robot will move to the highlighted P variable with P2P interpolation. This means the robot will take the coordinated move path as quickly as allowed, even.
Now there you can see point 0 and point 1. All right. So there are different coordinates, right? You can see over here, right? Left above, non-flip, and you can see these angles, right? Changing slightly, or for all 6 joints, right? So when you have number of points like that, P0, P1, P2, P3, P4, like that, and you have set the speed also, the controller can actually interpolate all the joint angles from point 0 to point 1, point 1 to point 2, point 2 to point 3, like that, interpolate it, and then create the reference trajectory as I explained earlier, and then take one at a time and implement it and send it to the servo controller for implementation.
If it requires the end effector to travel outside of a linear path. Linear interpolation follows a straight line regardless of the speed it needs to get there. Thanks for watching.
So it's much easier than you would have anticipated. Anybody can do that, okay? Now, there are questions. Now, the simplest technique is this teach pendant method. The device is called teach pendant because you use it to teach the manipulator point by point. And after that, it is interpolation. That is not the best trajectory planning, right? because when you have the piecewise linear curves, right, and one line is different from the other line and so on, there can be discontinuities in the wire points, so it will not be very smooth, and you have a lot of problems. But there are algorithms. These things have already been solved, and a lot of research have been done, development, and there are built-in algorithms to make very smooth trajectories. Okay, so trajectory planning is another area in manipulators. You use not only the piecewise linear curves, but spline, parabolic curves, trapezoidal velocity profiles. You can bring them in and plan a very smooth trajectory. Okay, so these are built into the system. When you specify 0.01234, everything is happening internally. You don't have to worry, right? And sample trajectory that is being generated would be very smooth. Now, after all these things, right, like say you teach a particular trajectory, maybe laser cutting, welding, or whatever, using the teach pendant, right? You're pretty sure that this is gonna execute. But it's always good if you have a simulator, and not every manufacturer gives you a simulator, right, when you purchase a manipulator. But if at all possible, right, it's good to have a simulator, and then you can simulate the trajectory, okay, what you have planned, and see for yourself what's happening. So that'll give you an extra sense of confidence, right, that what you have planned is probably feasible, and it will not generate any problems, right? This is the standard practice. And after doing that, you can bring the trajectories directly to the manipulator and implement it. So as you saw in that video, there's no such simulator. Once you implement point by point, right, you can directly execute it. Yes, that's actually a simple trajectory planning process. You don't need to go through the simulation. You can directly execute the path. Now, where are we in the on the robotics landscape? That's also very important to understand where we are right now. So we have come from, say, as far back as 60s in industrial manipulators, robot arms, manipulators in the factory floor, very dangerous machines, right? Nobody wants to get close to these manipulators. But today, it's different. Now, robots have the capabilities to be very safe to humans, right? Even if something goes wrong, it will not be very hazardous to people around the robot. So we are actually heading to human robot collaboration in the future, near future, right? So even the material you're going to use for the robots is going to change. You can see it over here, right? This is different from the looks and feel of industrial manipulators. Not only the material, the appearance, etc., the control systems are also going to change to what is called impedance control, hybrid control, compliance control, like that, right? So that it will be not only position control, but position and force control together. So there's an additional sense of contact force, right, to make it like safe for the nearby obstacles and people around it, right? And also you will see compact and easy to use robot systems, right, being developed, and also energy efficient and very much user-friendly systems. For example, if you look at the 80s, 90s, it was a very big decision for companies to acquire robots because uh, it was not easy. You need to have an engineer with a lot of knowledge about manipulators to make use of the manipulator. But nowadays, as you saw in the video, anybody can install and make use of a manipulator because the teach pendants, the software that is coming with the robot, user interfaces, they're all developed to a significant level. So it's like an advanced toy now, right? Rather than a sophisticated machine. The manipulators have become have changed to the state of advanced toys. So this is the landscape we are in right now. So then you have some statistics I explained to you the other day. Then I want to discuss with you this one, factory robotization. So again, this is a very significant topic for you. Let's say you have a company, you have a factory, right? And you use some machines, some people working there. You are manufacturing some products, right? And at what point you're gonna decide, okay, it's time to go for a technology transformation. So we are going to robotize the factory, which means you are going to bring in robots and configure them, install and configure them, and you're going to run your manufacturing process using robots, right? Maybe 50%, 70%, 80% robots, whatever percentage, right? So this decision is very serious. So what are your reasons to go for factory robotization? Why you want to bring in robots, right? You need to have a informed decision here. So I can provide you some hints, some bullets, right? Like first one, declining cost of robots. Declining cost of robots and increasing cost of human labor. That's one of the major reasons as to why companies or factories want to use robots than humans, because human labor is only increasing, whereas the cost for robots is declining. So you have two lines. One line, it starts at a higher value, like robots were very expensive earlier, but now cost is getting down. So it's a line which is going down, right? It's a line which is going down. So one line is going down like that. But if you look at the human labor, I think it was very cheap back in the day, but now it's increasing. So you have human labor going like that. So at some point, you will see the break even, right? So after that point, it would be easier or cost effective using robots than keeping human labor, right? I'm not talking about every sector of the employees, but certain sections, right? It would be easier to bring in robots and it would be cost effective as well. Number two, second bullet, robots continue to getting speed, accuracy, capability, and reprogrammability. Again, if you compare the present day robots with the robots that were there in the 80s, 70s, right? So present day robots are faster and more accurate and have a lot of capabilities and also very flexible. Programming is easy. So earlier, 20 years ago, 30 years ago, it was a difficult challenge for companies to install and make use of robots. You need to maintain the system very carefully, and only fewer people knew about how to maintain the system. But nowadays, as I just explained, robots are like advanced toys. Anybody can maintain a robotic assembly line, right? And they are much more faster, accurate than their predecessors. So naturally, factory owners would like to invest on robotization. And number three, some tasks which are inherently hazardous for people. So if you deploy people, it would be very costly. Now, these days we have the COVID thing. We don't see many people with the complete kit nowadays, right? Because with other reasons. But if you remember, about a year ago, it was a hazardous duty out there, right? The full kit and all. But what if you have a robot to do that? Right? You don't have to worry. Deploying robots for dangerous and risky operations, right? Anyway, you have to do that. If you are handling a nuclear or radioactive material or hazardous chemicals in your industry, you better have some machines or robots, right? And also depending on the environment, if it is a space operation, you definitely can't use humans. You need to have robots. If it's undersea, again, you need to have some sort of machine or robot to do that. So these are the frontline reasons for many companies to roboticize their factories. But there are other reasons also. A lot of companies, they need to they would like to not to have labor problems. They don't like to have strikes by the employees. They don't want to have demands for higher salaries, etc. Right? So this is a very controversial topic, but that is the reality. So most of the companies would like to have robots so that they can make use of the machines 24/7, right? And with a little minimum set of staff so that you don't have this a lot of people demanding some salary hikes, and also they are working 8 hours a day, whereas machines work indefinitely. So these are the other reasons as to why factory owners would like to have robotics and other automated machines at the first possibility, right? And this graph shows you that break-even point uh, between human labor and automated machines and robots, right? This is a very famous graph, very generic one, not too specific to any industry. This graph shows you the production volume and the unit cost. Very generic, okay? Very generic. So if you use manual labor in your production lineup, so no matter how big or small your production volume is, the unit cost stay flat. Whether it is a small quantity or large quantity, the unit cost stay flat if you use manual labor. And that's why when you go to higher production volumes, you don't want to have manual labor, okay? Because there are other cost-effective options. There are two options. One is hard automation, and the other one is soft automation. So let me talk about the hard automation first. Hard automation is not robots. Robots are flexible in the sense you can change the code, change the end effector, and use the same machine, the robot, for various other applications. Say, for example, you have a manipulator for laser cutting and you change the end effector to welding torch. Probably you can use it for welding. Not as easy as I explained now, right? But the possibility for flexible or changing the application is there for robots. So if you use robots, depending on the production volume, your unit cost will drop like that. Robots, soft automation, right? But hard automation is where you use a specific machine just for that application. You can't use this machine for anything else. It is kind of hard coded, custom designed for that application. So because it is custom designed for a particular application, on one hand, it doesn't have any flexibility at all. That is a negative side, but the positive side is it is the most cost effective machine for large volumes. Because this machine is expensive. Right? Having this machine, proprietary machine, sometimes for a specific application is very expensive, right? But if you have large volumes, it has the lowest unit cost. So this is how the three graphs intersect each other. One is flat. The soft automation, which is using manipulators, starts somewhere here, right? But it will drop quickly below the manual labor cost, and it will stay flat like that for production, higher production volumes. But the hard automation is much more expensive than having robots because the machine is very expensive, but it quickly drops the unit cost, and at some point it will cross over with the unit cost of if you have the robots. So when you read this one, you can see 2 points of intersection, actually 3 points of intersection there. What is most important for us is only these two intersections, right? The first one where the soft automation crosses the manual labor line. So if your production volume is under V1, you better go for manual labor. Don't worry about robots or hard automated machines. Just employ some people and implement your production. If your production volume is very small, below V1. But if your production volume is between V1 and V2, the most cost-effective technology is robots. Use manipulators and do the job. And if your production volume is beyond V2, you better use a specific machine designed for that specific application. Okay. This is generally true for most of the manufacturing processes. Right. So that's about it. Any questions? Any questions, please? All right then. I will upload the 3 video lectures and the lecture notes also to the Moodle, and you will get automatic notification so that you can download the material and study. Right. So then if there are no questions, we will wind up for today, and I'll see you next Saturday. Have a good night.
Good night, sir. Sir, good morning.
No, I'm back in Sri Lanka.
I said good night. Thank you.
Thank you.